Welcome to another video for physical science. In this video we are talking about electrical energy generation and transmission. Actually, going back, you'll notice I have some transformers. You'll see why in a minute. So let's first talk about Michael Faraday. Michael Faraday lived 1791 to 1867. He developed what's called Faraday's law. He discovered electromagnetic induction in 1831. And this particular discovery paved the way for many practical uses, many practical technologies that we'll discuss in this video. So electromagnetic induction. The definition of this is generating a current by moving an electrical conductor relative to a magnetic field. So let me demonstrate what this is referring to. So as I begin this discussion, let's first discuss or take a look at the magnet and the effects that it has. So here you can see that the magnetic fields are turning the compass, right? So there's a magnetic field on this magnet that's pretty obvious. And then we're going to add a coil to it, okay? In fact, I'm going to add 3 loops to this coil, okay? And you'll notice that the blue lines here are the electrons. Now notice what happens when I move the magnet through the coil. Okay, so when I move the magnet through a coil, this is what's called electromagnetic induction. This is what Faraday was referring to, is that when you move a magnet, the magnetic fields, which as you can see, the magnetic field lines surrounding the magnet, what they do is they have an effect on the electrons in the metal coil, and they cause movement of those electrons. And as you can see, that movement of electrons causes, as we know, electricity, right? So we were able to power the bulb on and off. And this is what he was referring to. So you can move the magnet relative to the coil, or you can move the coil to the magnet, and you still have the same effect. Okay, so this is electromagnetic induction. So by definition, Faraday's law is a voltage is induced in a conductor by a changing magnetic field. Okay. Now I can have a light bulb. I can also have a galvanometer, which is what your book has. You can see there's a resistor there to take the voltage. So you have a voltage that's created by the movement of a coil relative to a magnetic field. Okay. Now what would be cool is that if I could have some kind of mechanism that would move either the magnet or the coil so that I could generate electricity, because as you can see here, I'm the one who's moving the magnet, and I'm probably wasting more energy than I am producing by moving the magnet back and forth. Okay, so what I'm going to do, go to the generator. As you can see here, I have a generator that's already spinning, and you'll notice that the magnet that's on this wheel is turning, and the north-south poles are switching sides. And as that happens, that magnetic field from this magnet is pushing the electrons back and forth, causing an AC current. And as you can see, that's powering our light bulb. So what I can do is I can turn up the current, which spins the wheel, or our turbine, and basically all our power plants are built off of this principle thanks to Tesla, where you have a massive turbine that's being spun by running water. So here you have a little image of a hydroelectric plant. You have the intake here where the water flows. It spins the turbine where the coil is being spun, and the electricity is being generated and pumped into a transformer, to a step-up transformer, into our transmission power lines and into our neighborhoods. Or you can also have turbines that are spun by wind power, and they can be spun by current wave, water wave current power. And so as these turbines are spun, now usually it's actually the coil that's being spun around situated magnet. But in this case, you can see that we have a magnet that's being spun around to create that effect that we're looking for. And I'm going to add another loop to increase the effect. And I can see I can add a galvanometer as well. And you can see the alternating current going back and forth. So let me back up. So again, this is a generator. This is a turbine. This is what electromagnetic induction that Faraday was referring to. Let's take a look at an electromagnet here. Now you'll see here that we have a battery that's a 10-volt battery. I'm running a direct current through this wire. So you're noticing that the electrons are moving. Now if you recall from section 2, a coil, when I have a coil and I have electrons that are being run through it, I have an electrical current, that's what's called a solenoid. Okay, and so my solenoid, as my electrons are moving through my coil, they're creating a magnetic field. They're creating, so essentially what this becomes is a magnet of sorts. And you can tell as I move around my coil that the compasses are being moved around, which means that there's a magnetic field that is influencing them. Okay, so this is again an electromagnet. This is a magnetic field that's being generated by electron movement in a coil. And again, that is called a solenoid. Now let's take that solenoid that we have produced. And again, this is pretty much a magnet. And as you remember from our coil experiment here, we had a magnet moving through a coil, we generated a current. Well, likewise, again, this is pretty much a magnet now, thanks to the current running through the coil. Now I can do the same effect that I did with the magnet in my previous demonstration. Right, so I have a solenoid going through a coil, and as you can see, I am still having the same effect, an alternating current effect, where I'm able to produce electricity because of the magnetic field lines that are being produced by my solenoid here. Okay, so as we conclude this video, we're going to now talk about transformers. No, not Hollywood transformers, but electrical transformers. Here I have two types of transformers. I have a step-up transformer and a step-down. The way you can tell the difference is by looking at the incoming. Okay, so if you look at the top image, you look at the blue arrow on the top image, you see that there's enough coils there. The primary coil has 10 turns around our metal there. Okay, and we have 60 volts that are coming in. And those 60 volts are being stepped up to 120 volts. So if you look at our secondary coil on the right side of that, you see that secondary coil, you have 20 turns. So that's double the amount of turns that you have on the incoming, the primary coil. So because of the increased amount of coils, this is regarded as a step-up transformer. So I bring in 60 volts and I step it up to 120 volts. Now, if you look at the bottom image, you see there that we have 40 turns of the wire. That's 240 volts that are coming in. Okay, 240 volts, but then if you look at the secondary coil, it's been reduced to half, to 20 turns of the wire. So it's been decreased by double, 2 times. So that decrease in coils decreases the amount of volts that go through. So you'll notice that on the red arrow, on the right side, you have 120 volts going out. That's a step-down transformer. Now, how do these apply? Step-up transformers you'll find in power plants, where you want to generate enough power that can enough power in the power grid to take into your neighborhood so that each home can have sufficient power. But if you look at the power lines can have up to 8,000 volts of power, and that's way too much for your common appliance in the house. So then you have step-down transformers in these power lines. So if you go outside in your neighborhood and you look at power lines, you're going to see these huge boxes, and these are called step-down transformers. So let's take a closer look at that transformer so you can kind of see part of the machinery at work here. So this is our step-down transformer. Now if you look at the primary inputs, okay, I'm going to put an arrow there. Those primary inputs, those have 7,200 volts coming in. Okay, again, that is not safe for your common household appliances. Even the most powerful ones like your stove, electrical stove, or electrical dryer, clothes dryer, this is way too much. So you have secondary outputs. These secondary outputs, the secondary coil will be much less than the primary, stepping down the amount of voltage to a much more manageable 120 to 240 volts for your common house. So this is a step-down transformer, and these are applied to your common neighborhood, to your everyday neighborhoods, where and how the power lines are stepped down to produce power for your appliances at home. Okay, well that does it for our discussion in electrical energy generation and transmission. Good luck in your studying.